Hello, we are Kyle Charty, Tristan Townsend, and Alexandra Westbrook. The issue we will be talking about today is arsenic contamination of groundwater in the Red River alluvial tract in northern Vietnam. Arsenic contamination poses a significant health threat on a global scale. The World Health Organization, WHO, has set the drinking water standard for arsenic concentration at 10 micrograms per liter, or parts per billion. As can be seen by the figure, there are copious sites interspersed around the world where concentrations are above this threshold. In many cases, multiple orders of magnitude higher concentrations, up into the parts per million level of concentrations, affecting hundreds of millions of people. This can have serious detrimental effects on people consuming this water, especially as their consistent drinking water source without access to a filtration system. Arsenic contamination has been linked to a number of different cancers, including bladder, lungs, skin, kidney, nasal, liver, and prostate cancer. Non-cancerous effects include, but are not limited to, partial paralysis, blindness, thickening and discoloration of the skin, as well as diarrhea and vomiting.
Vietnam is in Southeast Asia and its citizens are governed by a single-party communist state. Because of the authoritarian regime in the country, it might be difficult to implement wide-scale policy changes regarding issues affecting vulnerable populations like rural communities. Vietnam has experienced some of the fastest rates of economic growth globally, so income stratification is readily apparent across society. Rapid urban development has actually threatened to marginalize and exclude traditional subsistence farming populations. Additionally, gender inequality is prevalent within the Vietnamese society, and inegalitarian gender norms persist based on the desire to preserve cultural traditions. The Red River Delta, which contains the capital city of Hanoi, is one of the most densely populated regions in the world, with 2,171 people per square kilometer. Groundwater is the primary source of water for those living in the delta. However, roughly 11 million people out of the 16.6 million in the region don't have access to a public supply of water and instead have to rely on private tube wells.
So here's a bit of an overview of the problem. Arsenic contamination has been a historic issue in both the Holocene and Pleistocene aquifers of the Red River Delta, which is the source of drinking water for 7 million rural Vietnamese people. The average arsenic concentrations in the Red River Delta were historically 159 parts per billion on average, but they range from a low of 1 part per billion to a high of 3,050 parts per billion. And as you can see, this is far above the Vietnamese standard of 50 parts per billion and even further above the WHO standard of 10 parts per billion. Although the source of the contamination is geogenic, the perpetuation of the problem is anthropogenic because large-scale pumping has led to vertical migration of this contamination, which magnifies the risk and the number of people affected. Access to safe drinking water for the people of northern Vietnam is both an environmental and an economic issue that calls for the implementation of an efficient plan of action and a cost-effective solution.
One possible solution is blending of waters to optimize the efficiency of arsenic removal. The equation shown below shows a simple relationship for assessing the arsenic removal, which infers a preferential removal of phosphate over arsenic by sand filtration. In this equation, M denotes a concentration in moles of iron, arsenic, and phosphorus, respectively. It was determined that values above 54 are needed for efficient arsenic removal. Thus, blending of water from wells with a high R value with water from wells with a low R value can be done to optimize arsenic removal efficiency. Determination of any regional trends within areas of elevated arsenic concentrations and divisions of high and low R value areas can be made to improve arsenic removal efficiencies, as well as to be able to map final arsenic concentrations in treated water. Another possible solution are household sand filters. These are already widely used within the Red River Delta to mitigate arsenic removal in pumped groundwater. An example can be seen in the figure that arsenic, iron, and bacterial concentrations are all ameliorated through this process. These systems are ideal for people who are not currently covered by a centralized water supply system, such as those residing in rural areas. Sand filtration also does not require extensive supplies to set up. It is simple to implement and does not require power to operate. The downside to this is that it does require perpetual physical input of labor to filter the water. Additionally, in densely populated areas, such as Hanoi, this proposed solution is not ideal to implement as an overarching solution.
Another possible solution is treatment by chemical precipitation. Chemical precipitation is the process by which a chemical reaction of two or more compounds forms a solid called a precipitate. The process of arsenic precipitation in particular involves the addition of alum, lime, ferric, or a combination of compounds to form an arsenic-based precipitate. And following precipitation, sedimentation and filtration can be carried out to get higher removal efficiency. So some of the advantages: in the presence of chlorine, which also provides disinfection, this process returns a removal rate of greater than 90%. Chemical precipitation is permanent and can assist in removing other heavy metals from drinking water. And also, chemical precipitation can be carried out on a smaller scale using a bucket and a mixing stick, which may be more feasible for rural areas. And some of the disadvantages include that chemical precipitation on a community scale practically requires the construction of an entire water treatment plant, including a reaction vessel, a chlorine retention tank, a sedimentation basin, and filters. Construction and maintenance of this system, including monthly purchase of chemicals and electric power, is costly. Also, this process is pH dependent, which requires monitoring and possible addition of more chemicals. And finally, this process creates sludge, which must be removed and disposed of. Another solution at the community scale is treatment by membrane filtration. And we looked into 3 types of membranes, which is reverse osmosis, nanofiltration, and microfiltration, with the following pore sizes. Some advantages is that nanofiltration and reverse osmosis are the most effective at removing suspended and dissolved arsenic, since the pore sizes are very small. Also, reverse osmosis and nanofiltration can achieve arsenic removal rates of greater than 95%. And a system that combines chemical precipitation with coagulation, flocculation, and microfiltration is the most effective, which returns arsenic removal rates of 99%, but again, this is very costly to construct. And the downside of these technologies, especially reverse osmosis, is that it requires a very high pressure and electricity input to push the water through the tiny pores. Also, membrane technologies require significant maintenance as clogging becomes an issue. And as mentioned before, the system is costly to construct and maintain. Another possible solution is to exploit a different source for drinking water, which could be rainwater harvest. So some advantages is that rainwater is very available in the Red River Delta, especially in the monsoon season from May to November. The annual average precipitation is 190 centimeters each year in the Red River Delta. And actually in the rainy season there is too much water because flooding in the city of Hanoi is a big concern. And you can see an example of that flooding in the picture on the right. So construction of rainwater basins could potentially provide storage to mitigate for some of the flooding, as well as provide a source of arsenic-free water. And this can be done on a community or an individual scale. Some of the methods of rainwater harvest at the community scale include construction of reservoirs, use of underground cisterns, digging of collection wells, among others. And finally, rainwater harvest is less costly than remediation of groundwater, especially at the individual scale. Some downsides to rainwater harvest is that there's not a constant supply of rainwater. It's based on daily weather patterns, so in the dry months there may not be rain for days or even weeks. Another downside is the predictions of climate change for the future, because weather extremes are expected to intensify. Therefore, the droughts in the dry season will become more severe, and that could affect the potential for rainwater harvest.
So, one possible solution could be installing community based adsorption treatment units. The units would be installed at the top of existing wells and attached to the hand pump, which allows for consistency in villagers' method of water collection. The unit is a stainless steel column filled with adsorbent, and when water flows through the unit, arsenic is then adsorbed to hydrated ferrous oxide precipitates. Then the adsorbent at the bottom of the column would take up any remaining arsenic in the water and also trap the arsenic-laden HFO particles. So these units do require backwashing of the HFO particles every other day, which would then get trapped on top of a coarse sand filter. But they wouldn't require any electricity, addition of chemicals, or pH adjustment for their daily operation. Previously, these units were installed in Indian communities, and in each location, the villagers formed water committees to manage the treatment unit, and these committees always included women. The units were able to reduce arsenic concentrations to below 50 parts per billion, which is the Vietnamese standard, while simultaneously engaging community members. Because of the high cost of installing these units, an investment for their initial implementation would be needed by the Vietnamese government or an NGO, but their operational costs would then be covered by a monthly tariff from water users. Switching from arsenic-contaminated groundwater to surface water is an alternative to consider. However, it's imperative to avoid citizens' exposure to bacterial diseases since the risk of dying from these is actually greater than dying from arsenic poisoning. There's evidence to show that hygiene education and sanitation provision is actually more successful in reducing diarrheal incidents than investments in water quality alone or water quality and quantity together. Studies following hand washing education and the provision of soap, as well as point of use treatments, show 40% and 20 to 30% reductions in diarrheal incidents, respectively. These chemical disinfection treatments could rely on simple household bleach or other methods using flocculants, adsorption, filtration, boiling, or solar disinfection. Hand washing campaigns coordinated by the Vietnamese government in conjunction with point of use treatment offer significant reduction in bacterial contamination of surface water with no infrastructure investment necessary. The caveat with this solution is the health hazard posed if educational campaigns fail or if chemical treatment is done improperly. A hand washing campaign already done in Vietnam wasn't the most successful, but soap wasn't provided to families at all, so that would definitely need to be done in any future campaigns. So, further combining these methods with other low cost methods of water treatment could allow switching to surficial sources to be a low cost alternative to arsenic contaminated water. Our final solution is site, temporal, and context specific. Obviously, not every solution may be appropriate for different areas within the Red River Delta region, and we'd hope that previous site evaluations could be used to determine the best solution for each area. But our general solution proposal is split between rural and urban areas. So, this is because of the stark difference in the way of living that exists between these community types, as well as recognition of the way that government funds might want to be allocated. So, better provision of services to urban hubs versus to rural communities. So for rural areas, we recommend using a combination of rainwater harvesting, sand filters, and educational outreach programs. During monsoon season, rainwater harvesting could be the primary source of water since there will be significant rainfall. During the rest of the year, when rainfall is variable, relying more on sand filters could be done. Having the government provide rain barrels and sand filters to these communities could be done at a relatively low cost. Furthermore, the government should develop educational outreach programs like hand washing campaigns to limit bacterial contamination of harvested rainwater. For urban regions like Hanoi, we would recommend chemical precipitation. This is because of the constant availability of electricity in cities to provide for the running of a large treatment plant. Also, since there is existing infrastructure that provides a public supply of water to citizens, this centralized treatment option would likely be the best way to service such an enormous amount of people at once, despite its high costs.
The goal laid out by our initial vision statement was to maximally reduce the number of arsenic-related diseases and deaths in the Red River Delta. The motivation for this proposal was to improve public health, decrease physical and mental stresses, and increase life expectancy for the people of northern Vietnam. The solutions proposed in this paper are anticipated to remediate the arsenic problem in the drinking water of both rural and urban communities to the Vietnamese standard, and to bring about increased human health and livelihood. The longer-term goal is to meet the standards established by the WHO through upgrades, increased efficiencies, or applications of new technologies, especially in rural communities where the treatment is more decentralized.
In conclusion, we have detailed the severities and repercussions of the arsenic contamination of the Red River alluvial tract in Vietnam. Numerous possible solutions were proposed here, all of which could help mitigate the high arsenic concentrations and greatly improve the quality of life for the inhabitants of the area. We discussed blending of waters, sand filtration, chemical precipitation, membrane filtration, rainwater harvesting, adsorption, and switching to surface water alternatives. The final recommendation that was proposed was not a singular choice, but instead was specific to the site, the seasonality, and current state of contamination in each area. In summary, implementation of sand filters and rainwater harvesting, as well as incorporating educational outreach programs, was proposed for rural areas, while chemical precipitation was proposed for the urban center with highest concentrations in Hanoi.